This conference will now be recorded.
All right, guys. So today we're going to talk about cylinder heads, and we're also going to talk about engine blocks. And these are pretty much the biggest components of an engine. These are where all the moving parts, all the moving components of an engine are going to be our cylinder head and our engine block. And you may call these a top end. Our cylinder head is sometimes called the top end. The engine block is sometimes called the bottom end. Combined, they make what's called a long block, which means we have a bottom end, an engine block that's complete, and we have a cylinder head, a top end that's complete, and they're already combined. So you may hear the term long block. It means a head and a block combined. You may also hear the term short block. A short block is just an engine block with pistons, rods, crankshaft, all that included, but no cylinder head. So just a couple terms to throw out: top end, bottom end, long block, short block. Again, it depends on what you're looking for, what you're building, what you're looking to buy, who you're talking to, whether they understand these terms or not. So let's go ahead and get into our lesson here on CDX, and we will go ahead and get started. So right here, chapter 19 is our cylinder head components. So let's go ahead and get going with that. So we click on that, and down here there's not a lot of meat, if you want to say, in this chapter. This is a lot of here's what it is and here's what it does. Most of what you guys are going to learn and do with cylinder heads is going to be out in the lab, as far as removing them from the engine, taking components off of them, camshafts, removing camshafts or installing camshafts, valves, etc., etc. So, a lot of cylinder head work is just hands-on work. Okay, so let's go ahead and get started. So, cylinder heads and components. This is a good video. This guy has a cutaway cylinder head. I believe it's from a Ford. But he's explaining the components of that cylinder head, and also he talks about how a cylinder head is made. It's not, or most cylinder heads don't start out as a solid chunk of metal. Okay, some very, very expensive cylinder heads can and do. They start with a big chunk of metal, and they actually cut out and machine the passages and the ports in the cylinder head. Most of them, especially for normal cars, they're what's called cast, meaning they make a sand mold or a foam mold of what the passengers are supposed to look like. They put it in a box, basically. They pour metal in there and take the big chunk of metal out, vibrate it, the sand falls out, and then you've got passages and ports in your cylinder head. Then they obviously do finer machining after that. Or you can have something very similar to sand that's a foam core. They have foam, layers of foam that they build the passages and ports with. And again, they pour metal in there, and then this foam basically melts away, and you're left with the ports and passages. So he's going to explain how these cylinder heads are put together here after a commercial. Makes me not want to go to Tampa Bay.
Hi everybody, thanks for stopping down to Pete's Garage. I have about 15 minutes to tell you everything I can about cylinder heads. Now, most cast aluminum parts that are cast using the lost foam technology start out like this. This right here is a cylinder head. It doesn't look like a cylinder head because it's not made out of aluminum, but is a precision model of exactly what a casting of a cylinder head would look like when it comes out of the mold. This is how most, or actually all, lost foam technology or lost foam cast parts, this is how they start their life, and this, like I said, is a cylinder head. And this is what it is. This part, this cylinder head, as you can see, if you look, you see the parting lines here. These are glue lines right here. So this part is made in 1, 2, 3, 4, 5 different pieces. Okay, those glue lines are important to remember because I'm going to talk about those later, and the different pieces. The reason it's made in different parts like this and glued together is because there are passageways inside of the cylinder head that are extremely difficult, and it would be impossible to cast using traditional casting methods. So they developed this lost foam technology which enables them to make very complex parts with intricate passageways on the inside. Now, this is how this works. The part is made out of this foam, and this is a very precision foam used for this method, and it's a very specific density for the beads, and I won't go into that. But you can see that the top of the cylinder head, the exhaust side of the cylinder head, the face where the valves go, and the intake side, everything is exactly as it would be as if you were to look at a finished machined cylinder head. And again, this would be the raw casting. This is placed in a mold, and it is packed thoroughly with an extremely fine casting sand. Every one of these openings here, every one of these little voids gets filled with a very fine sand. It's packed in there, and then it's packed around with a regular kind of casting sand, and a sprue or a hole is left to go inside to the foam. Then what happens is when the molten aluminum is poured into the mold and it reaches the foam immediately vaporizes, leaves a void inside of the sand, and the aluminum takes its place. That's why it's called lost foam. It's lost foam because when the molten aluminum hits it, it vaporizes and it becomes lost, leaves a void, and what you have out of a mold is a finished cylinder head. Now, if I were to take, when this comes out of a mold, and if I had a finished cylinder head here, if I were to take the aluminum cylinder head and cut it with a saw, cut it and section out a piece of the cylinder head right here, I would end up with something that looks exactly like this. As a matter of fact, I'd end up with exactly this. This is what the aluminum cylinder head looks like after it comes out of the mold. And you can see, if I can, I will try and get here as close as I can so you can see. You can actually see the foam beads cast right into the aluminum. It looks like it's made out of foam. That's why cast parts that look like foam have that contour to them, or that sort of texture, is because it was produced using the lost foam technique. So here is a cutaway, a section of a cylinder head, and I'm going to use this to explain how a cylinder head works and what the valves do and how the different oil passages work and how the coolant makes it through its way through the cylinder head. Here's a close-up of the cross-section cylinder head. This would be the intake side, this would be the exhaust side, this is a spark plug right in the middle. If I turn it, you can see here's the valves right here. And if you remember, I was talking about the precision sand and the sand, very fine sand. You can see inside here where this water jacket is, there's a very fine sand and still inside the water jacket that needs to be flushed out. But this is not a finished cylinder head. So let's talk about how fuel gets inside the combustion chamber first. When the fuel injector is put inside the engine here, and it would be put in right like this, and it sits exactly right here, this black O-ring is the only thing that seals the fuel injector inside the engine. You only need one O-ring, and it's a very light O-ring. It's not that hefty. And if you get a cut in here, you'll get a lot extra air in your engine. The engine will run lean. The reason you don't need a hefty seal here is because as air comes in here through the intake manifold, and this fuel comes out of the injector sprayed as a mist, the fuel mixes right here, and this is a vacuum. So air is being sucked in through here past the injector. So this O-ring seals air from being sucked in. Now, as air comes in here, air comes in through the intake plenum, the fuel injector sprays a mist of gasoline right here, and they both come in, they both combine right here, and then they enter in through the bottom here into the intake valve. You can see the intake valve on the bottom. The exhaust looks very simple. You have the piston down here, the fuel air burnt, so you have your hot emission gases, comes up, exits right through this port right here. Here's the exhaust valve right here, and it comes out through this port right here. And the rest of this is coolant passageways. This is how coolant gets through the cylinder head to cool down the cylinder head as it's running. You can see the coolant passage here continues down, and it comes out the bottom of the casting. This would go through the block and continue in through the water pump and cool down the rest of the engine. So that's a cross section of the basic parts of the inside of the cylinder head. The top part, like I said, you have the two holes here. These would be for the Slaws or the lifters, mini lifters if you want to call them that. There's one on each side for the intake and exhaust.
Now he's calling these things slaws or schlaws. I don't know what part of the country he's from, but honestly, I've never heard them call that. We normally call them, he's calling them mini lifters. So again, I don't know where the schlaws term comes from, but what he's talking about is right in here is our valve is going to go right in here, and then right here we have what he's calling the mini lifter potentially. So, you know, I don't know what he's, you know, what part of the country he's from. So just bear with his terminology here.
Exhaust. These are where the valve springs will sit. Bolt holes for the cylinder head, and you can see the spark plug, how the spark plug sits inside like that. So if you're looking down at the top of the engine, you see both spark plugs. This happens to be a cross section between two cylinders, which is why you see two half cylinders. If you remember, when I had the foam part in my hand, and I said it's just the foam part is the mold for the cylinder head, and I said, remember those parting lines where the glue is. If I come in here and look real close, you can see here's a parting line right here. And up here, there's a parting line right in here, which is hard to see, but there's a parting line right there. There's a parting line right down here. There's a parting line right in here. So if you were to look at this and count, we have the pieces of the foam. One is down here. Second part is right here. Third part right here. Fourth part is right through the middle. And the fifth part is on top. So you can see the actual parting lines or where the foam was glued together, because it's cast right into the aluminum. So that's how the lost foam method works when you...
And if you see, it looks like foam. When he zoomed in right there, it looked like a piece of foam. Again, that's the pattern that was on that foam. As soon as the metal touched it, it vaporized, but the metal had cooled just enough to retain the pattern of the foam.
Cast aluminum parts or any kind of part, and that's why that method is used, because you can see how complex some of these passages are, and that you wouldn't be able to do this with a regular casting. So that's why that method was developed, and that's why they use that to make cylinder heads, because the insides are so complex. Okay, now I'll talk about the valve assembly and what holds the valves together and what the main components are. First of all, you notice they're different sizes. The intake valve is larger than the exhaust valve, always. The intake valve is always the largest of the two, because the intake is working under vacuum and it needs as much volume as possible, or largest valve as possible, to get as much air and fuel in as possible. And this is how it works. That's the valve closed.
And this is true for whether you have a multi-valve engine like this one, where you have 4 valves per cylinder, so there's 2 intake and 2 exhaust. The intakes are going to be bigger than the exhaust. If you have a 2 valve per cylinder, 1 intake and 1 exhaust, you're also going to have a larger intake valve than the exhaust. Again, the heat and the pressure inside the engine after we have combustion and our exhaust valve opens to let our exhaust out, we have heat and pressure behind it to push it out. We don't have that when we're intaking air. When we're drawing air into the cylinder, we don't have pressure behind it, so we have to have a larger valve to let as much air and fuel into the engine as we can. Now, the only exception for the intake valve is larger than the exhaust is perhaps if we had 2 intake and 1 exhaust, then the intakes might be the same size or slightly smaller than the exhaust. But again, multiple valves, 2 intake valves mean we can still pull in more air. The 5 valve cylinder heads, such as the Volkswagen or Toyota also had a 5 valve cylinder head, 3 intake and 2 exhaust. Those intake valves are smaller than the exhaust valve. So there are a couple exceptions, but if we have a 2 or a 4 valve cylinder head, our intake are always going to be larger than our exhaust.
That's the valve open, closed, open. Same thing with the exhaust. Now the exhaust valves are working under pressure. The the hot spent exhaust fumes are under pressure in the cylinder trying to be forced out. So you don't need a big valve. This is under pressure. So when the exhaust valve opens up, all the hot gases come out and are forced out to the exhaust. Okay? So intake valve is always bigger than the exhaust valve. These are the other major components of the valve assembly. These are the Slaws. I call them mini lifters. It's really not a lifter.
So those are what he's calling the Slaws. Again, it is technically a lifter. It doesn't necessarily lift anything, but it supports the rocker, which he's going to mention in a second. It does have a little bit of give to it. It does pump up with oil. So again, it's technically a lifter. The Slaws term, I don't know where he's getting that from.
It's where the roller follower rests on. This actually rests on the Slaw, and it pushes to open the valve because the cam sits on top here and pushes it down. So we have the Slaw. We have the valve guide. The valve guide is what sits inside. The valve guides are right inside here. And those are precision machined for concentricity. The valve guide has to be machined so that this valve is exactly in the center of the opening of the valve opening, or the valve seat. So we have our valve guides. It comes through our valve seal. The valve stem seal, this is an umbrella type seal. The valve stem seal is what keeps the oil from leaking down the top of the stem. And that sits right on top just like that. You can see the valve stem seal sitting right on top of the valve. So when it moves up and down, that's what keeps the oil that's on top here from entering into the valve. Then we have our springs, the valve springs. Now, valve springs come in many different sizes and many different shapes. Some of them are cone shaped. You can see there's paint on this one. Sometimes the paint means that it has to go a certain way. There is an up and down on valves, valve springs. This one does not. This can go any way, upside this way or this way, it doesn't matter. But some springs have to go in a certain way, and they're usually tapered on the top. And you have to make sure you put the valve spring in properly. That spring is put under compression. Then finally we have the cap. The cap is a retainer, valve spring retainer, whatever you call it. It has many names. That sits on top. The valve stem comes through there, and the entire assembly is held together with these little keys. And these are the most critical part of the valve assembly, because this is what holds the valve inside the spring on the retainer.
And commonly called a keeper because it keeps the valve in the retainer. So a key is a term for these. It's also a keeper.
And puts the tension or holds the valve in place so that when the valve opens, that's what pulls the valve shut, the spring shut. Let me show you how a valve goes together. I would normally start by taking the valve, inserting it in the cylinder head so that this part is the only part that would be exposed. The stem would be exposed into the cylinder head. Now, valves are made in two pieces. They're actually welded together. You have the face of the seal, the sealing part, which is the valve face, and you have the stem. The stem is a hardened steel, and the tip is hardened because that's the part that sees the most of the abuse. You have the rings in here for the keys, and then you have the shaft. This is actually welded together, and then it's spun and machined so that you have a smooth transition here where it goes through the valve stem, or I'm sorry, through the valve guide. But the assembly order is you would have this, and then the seal goes on top of the valve where it sits just like that. And then the next thing is the spring. The spring goes on just like that. So we have our valve spring, and then the retainer goes on top. Valve spring retainer goes on like that. Now, if you can see, this would come right out. The valve would come right out of the valve spring if I didn't have something to hold it in. And that's where these little keys come in. Now I'm going to take a very close picture of this so you can see exactly what these keys do and how they work.
Everyone is calling this the new $1 billion stimulus program. It's a brand new stimulus program that will literally pay you to get...
Valve keys are one of the most frustrating part of putting a cylinder head together because they're so small. And you can see the tip of my finger and you see how small that is. When you compress the valve spring, you got to set these in place. If you don't have the technique to get those in place, these things fall all over the place, and when they fall inside something or they drop it, they're really hard to find. But the key is tapered. You can see it has the grooves on the inside where it fits in the valve, and here it is sitting on the valve. So you can see how it sits in the groove, and it's tapered so that when this the valve retainer, the spring retainer is put on here. You have that hole there. The hole is also tapered. When that's put on there, and once the spring is there, that's what holds it in place. Those two keys in place there, that's what holds the entire valve assembly together right there. Okay, this is what it looks like when you have your valve in place. The spring is in place. And I'm going to turn it up here. I have the Slaw in place, which is the place where the roller rocker lifts, or the RFS roller finger follower. Now, this sits on here just like that. And the cam would be sitting in here, just like this. So pretend my finger is the cam. And the cam pushes down, which when the cam pushes down, it pushes this way, pushes down, and the valve opens up. That's how the valve opens and closes with an overhead cam. You got an overhead cam here, the valve gets pushed down, opens up, and in this case it's an intake valve, so it lets the fuel and air mixture into the cylinder. So that's how cylinder heads are made and how they work. Talked about the...
So again, that was a pretty good video of him breaking down everything, all the components inside of a cylinder head. So he actually did a pretty good job right there. So that is cylinder heads and components. I have another video of the areas and the function of a cylinder head right here. Let's take a quick peek at that.
Hi, my name is Dave Localio, owner of Head Games Motorworks. Today, we're going to talk about cylinder heads, how they work, the different components, and what their purposes are. There is more confusion about cylinder heads and cylinder head components than any other question I get. So, the more you know, the more you grow. These are cylinder heads. These particular cylinder heads come off an LS. LSs have two cylinder heads because they're opposing V8. When there's also V10s, same configuration, where there's two cylinder heads in a V formation. Next we move over to our Boxer. The Boxer, like a Subaru or a Porsche, has two opposing cylinders and they face each other. Then we move over to our inlines. Inline 4-cylinder here, like this Mitsubishi Evo. Also like a Honda, where the cylinder head sits on top of the engine. Then we have our inline 6-cylinder, like a Toyota 2JZ RB26 TB48, where the cylinder head sits on top and there's 6 cylinders. Then we move over to our W's. This is pretty much Audi German stuff, that they have 6 cylinders, but they put them all in one cylinder head and have a W formation. So we're going to start off here with, as you can see, there's two different size holes. The larger one is typically the intake, and the smaller one is typically the exhaust. This is not always the case, but more often than not, it is. This is a combustion chamber. And this combustion chamber goes into the valve seat. The valve seat is comprised of valve angles. This would be your valve job, or where your valve seals to. So you have a top angle here, 45, a bottom angle, and then a second bottom angle. And that goes into your bowl area, or as we call it, a pocket. There is the short side radius. This part right here is the short side radius, and it should be a radius. The short side radius, along with the bowl area, is the most crucial area of any cylinder head on the planet. Dreams are made and broken here.
And the reason for that, the reason that radius is so important is, again, we're trying to get as much air and fuel into the cylinder. So if we can get the air to bend around that radius and keep up velocity, we can make more power because we get more air and fuel in. If the air slows down or stagnates, then we lose power because we're not getting as much air and fuel into the cylinder as we could or we should. Okay, so that's what he means by dreams are made or broken. There is, it all depends on that radius. Now the manufacturers, the OE manufacturers, they don't always try their hardest to get that to be perfect, but when you send out a cylinder head to get ported or polished or both, that's what they're paying attention to, is those valve seats, the angles, and the radius as well.
So there's two parts, two sides of any cylinder head, and that would be the exhaust side, which is depicted here, and they're typically round in nature, or they're rectangular, but they're always smaller than the intake port, just like the valve we just discussed. And this is the intake side. It's typically larger to accommodate for air and fuel from the intake manifold to go through the cylinder head and into the combustion chamber. These are valve guides. Valve guides come in different materials. Their main job is to center the valve over the seat, and also to dissipate heat away from the valve. Moving on to the top of the cylinder head, you see there's two different configurations on the lifter. This is the lifter area. On this Lamborghini, it has a small lifter that will have a rocker to come off to the valve, whereas this EcoBoost, just like the Nissan GTR and many others, they have a bucket, and the lifter goes inside here, and the cam journals, this is where the cam rides. So these engines are what's called a 4-stroke engine. What happens is the intake valve opens, allowing a column air to come into the combustion chamber. And then during the compression stroke, both valves will be closed and the piston compresses the air and fuel. Spark plug ignites, creates flame travel as the piston's coming back down. And then during the exhaust stroke, the piston comes back up, the exhaust valve opens, and it pushes everything out the exhaust port. Then there's the deck surface. The deck surface is responsible for keeping this all enclosed inside the combustion chamber via the head gasket. This surface must be perfectly flat and also of the right surface finish in order to hold the head gasket. Now we covered some of the basics, we can move on to some of the cooler stuff. Check us out on Instagram, Head Games Motorworks on Instagram, Head Games Motorworks on Facebook.
So there, he did a good job explaining the areas of the cylinder head. So all of these areas are important. Right from how the valves seal to the finish of the cylinder head, where the cylinder head meets the engine block. That area has to be perfectly flat, perfectly smooth, perfectly straight to get a good seal, because if we have any kind of warpage, and this is something I'll explain once we're out in the lab, if we have any kind of warpage, you have the risk and the potential for it not sealing, and you'll blow a head gasket. Even if you just replaced one, that's a common mistake. People that replace a head gasket on an engine, they don't send the cylinder head out to get machined, to get these areas made perfectly smooth and flat. They replace the cylinder head gasket, and a couple months later, or a couple weeks, or even a couple days, they blow the head gasket again, and they wonder why. It's because they didn't have that surface straight. So that's a very, very, very important thing to have looked at, repaired, or if it's too bad, you have to throw the cylinder head away and get a new one. Okay. So now we go into explain the role of a camshaft in an engine. Well, a camshaft is basically what we use to open and close the valves. So if you recall, on each of these chapters, if we go down, there's the media gallery right here section. This is where animations, videos, images are all in here. So if we were to click on this media gallery right here, then this would pop up. Okay, this is the media gallery itself. So if we wanted to look at what the function of a camshaft is, we would click cam lobes. Oh, this session has been logged out. Excellent. Excellent. Okay, so let me try to open this again. We'll click on it right here.
The cam lobe performs 3 jobs. It opens a valve at the proper time and gives it proper lift. It lets it stay open for a sufficient time. Then it lets it close at the proper time. Accurate valve timing is crucial. Valve timing can vary from engine to engine, as set out in manufacturer specifications in the valve timing diagram. The shaft of the cam is called the cam profile or contour. With the valve lifter resting on the base circle, shown as A, the valve is fully closed and there is clearance between the rocker arm and the valve stem. The cam rotates. The nose of the cam, B, reaches the valve lifter, and the valve is fully open. The closing flank, C, closes the valve gradually so that it doesn't pound against its seat. On engines without valve lash adjusters, a quietening ramp is built into the shape of the cam. This makes for quieter operation during the opening of the valve. The shape of the nose determines how long it stays open. The camshaft must always be synchronized to run in time with the crankshaft. This can be done by gears, chains, or toothed timing belts. Gear drives are most common in engines with the camshaft in the cylinder block and in heavy-duty diesels.
Okay, so there was our lobes explained right here. So let me close this guy. So that's how a cam works. We have a lobe, it spins around, and as it's egg shape, it comes up, the egg pushes on a lifter, a rocker arm, or directly on the bucket of the valve, and the valve opens. And as the egg shape moves around, then the valve is gently allowed to close. Okay, so overhead cam engines right here. Let's watch this guy real quick here.
In modern engines, the pushrod system is being replaced by the simpler overhead camshaft arrangement. The overhead camshaft is located in the cylinder head. There can be 1 or 2 camshafts. Let's look at a single overhead camshaft arrangement. Single overhead camshafts can use rocker arms. The cam can lift one end of the rocker arm, or it can press down on the rocker arm. On double overhead camshaft systems, the most common arrangement is to use a bucket tappet or lifter. It operates in a guide that protects the valve against side thrusts, which it would receive if the cam operated directly against the valve. The adjustment of valve clearance is usually done by changing accurately machined spacers. Spacers are available in a range of thicknesses, and they're exchanged to obtain the correct clearance. Some overhead cam engines use a hydraulic lash adjuster to reduce lash in the valve train. They have zero clearance at the valve stem, so there's no need for tappet adjustment. It can be put in the valve end of the rocker arm. Like the hydraulic valve lifter, it has a body with a plunger held against the valve stem by a spring. Oil supplied to the adjuster keeps the plunger in contact with the valve and eliminates lash. Lash adjusters can be put in the cylinder head at the end of the rocker arm. The lash adjusters are stationary and have a pivot for one end of the rocker arm. The plunger in the adjuster,
And this lash adjuster, or it is a lifter in a way, this is what that guy was calling the Slaws in that video.
holds the rocker up against the cam. In the lash adjuster inside the bucket tappet, the plunger's hydraulic action holds the bucket body against the cam on the camshaft and also against the tip of the valve stem so that there is zero clearance.
So there's how an overhead camshaft engine, how the camshaft works. Okay, so there was how a cam operates, the role of the camshaft, the operation of valve train components. We talked about gaskets, seals, and sealants. Well, you have to have gaskets. Anytime we have two machined surfaces put together, we need something to seal it, because even though they can be perfectly flat, metal does not seal with metal. So basically what we have to do, we have to have a gasket to help seal these areas together.
Gaskets form a seal by being compressed between stationary parts where liquid or gas could pass. Most gaskets are made to be used only once. They can be made of soft materials such as cork, rubber, paper, or asbestos. They can also be made of soft alloys and metals, such as brass, copper, aluminum, or soft steel sheet metal. Choosing which material and design to use depends on the substance to be sealed and the pressures and temperatures involved, and the materials and mating surfaces to be sealed. Head gaskets seal and contain the pressures of combustion within the engine, between the cylinder head and block. They also seal oil passages between the block and the head, and control the flow of coolant between the block and the head. Some gaskets provide or adjust clearances. Some joints between surfaces on modern engines are being sealed with special sealants, which eliminate the use of gaskets in some applications. Gaskets around a rotating part would quickly wear out and leak. To seal these parts, oil seals are needed. Many different kinds have been developed, including oil slinger rings. The most widely used is the lip-type dynamic oil seal. It has a shaped dynamic rubber lip that's held in contact with the shaft to be sealed by a circular coil spring called a garter spring. A similar sealing principle is used to seal the valve stem to prevent oil from entering the engine combustion chamber. Rotating or sliding shafts can also be sealed by using O-rings, but generally they are not as durable in most applications as the lip-type seal. As a general rule, oil seals must be replaced when a component is overhauled.
And that's true of most gaskets. You very rarely do you want to try to reuse a gasket, because many of them are one-time use only, especially a cylinder head gasket. Doesn't matter if you just put it on and tightened it down, and you're like, oh, I forgot something, so I have to pull the cylinder head back off. Guess what? That gasket is now used. You need to throw it away and use another one. Why? Some of these gaskets are made to crush, to fill in certain areas. They can only be crushed once. So again, gaskets, usually one-time use. Seals, one-time use. Okay, so that's what gaskets, seals, and sealants. We can use sealants, chemical sealants, silicone, RTV, anaerobic sealants to seal engines in to replace gaskets. Follow the manufacturer specs. Okay, don't just say, oh, I got RTV instead of using this gasket. Follow the manufacturer specs. Follow the repair manual. Okay. Describe the process of removing, inspecting, and diagnosing cylinder heads. Okay. Well, we're going to look at measuring the flatness and finish of a cylinder head. Okay. This is something we're going to be doing in class when we get our cylinder heads off. After this commercial.
Hi, I'm John Gernig of the Felpro Field Test Garage, located in Skokie, Illinois. And I've got an important tip for you today on checking the flatness of your cylinder heads before you put them back into service when you're using an MLS or a multi-layer steel head gasket. So I've got my straight edge, got my feeler gauges. I'm going to start with a 1/1000th feeler gauge. The spec on this cylinder head is to be no more than 4/1000ths out of flat across the entire length of the head.
So I don't know what kind of engine this is or cylinder head. Look at the repair manual. They're not all 4/1000ths of an inch or whatever he said the spec was. But we're using a straight edge. That's what he's using that looks like a ruler. It is a precisely machined piece of metal. It's not a ruler. It's not a pry bar. It's not a flat piece of cardboard. It's a precisely machined straight edge. Okay, you need one. We're also using feeler gauges, and we're actually putting a feeler gauge in the area between the cylinder head and that straight edge. And if that feeler gauge fits, then we try to go up to the next thickness until it doesn't fit. And then we say, okay, well, the last size that fit is X thickness. There's our tolerance. There's our clearance that we have. And again, it has to be within spec, or otherwise we have to machine the cylinder head.
I'm going to be checking this head in a variety of areas. I'm going to go across the middle as well as on a diagonal on each end, and then that way. So I'm going to get started here with my 1/1000th feeler gauge, checking across the center. That was good. I'm going to go on a diagonal. It's important that you make sure that you check for flatness no matter what cylinder head gasket you're using, but especially on an MLS, to make sure there's no out of flat conditions that will affect the sealing performance of the head gasket. So far, not finding any areas that are going to require this head.
So you see what he's doing. He's poking. Nothing's going in. The feeler gauge doesn't fit. That's excellent. That's what you want.
To go to the machine shop to be straightened out. So we should be in good shape here. There's a little 1/1000th area there right in the center, but a 2/1000th gauge won't pass. So that's acceptable. So we've got a good head. Next, I'm going to be checking the surface finish on this head to make sure that's within specs. So I have a 4-cylinder aluminum head here and a handheld profilometer that I'm going to.
So what he's going to use now, this is to, in certain gaskets, need a certain surface finish, a certain smoothness or roughness so that the gasket seals. This tool does that. This tool tells you if you're smooth enough or not. This is not something you would have. This is something a machine shop would have, and they would be able to machine the surface of this cylinder head to match whatever the manufacturer said it needed to be.
I'm going to use to check the surface finish of this head in various areas to make sure that the surface finish is within the specs that we call out for our MLS head gaskets. Now the specs that we call out is a 30 to 60 RA surface finish to accommodate the coating that's on our Permatorque head gaskets. So I'm just going in different areas of the cylinder head with my gauge, and it will go across, and it takes a reading of the surface finish in an RA reading to see what the finish is of the head. So I do this in the armor areas. I'll do this at the oil drain back areas to make sure that this cylinder head can be put back in service. So far all the readings that I'm taking, they're in the 20 to 30 RA reading. So that means this cylinder head is well within the spec that we call out, which is 30 to 60 RA. So I'm going to put this head back into service. So I'm John Gurnick from the Felpro Field Test Garage. And
so there we go. So again, machine shop should be able to do this if you are unable to at home. But again, resurfacing cylinder heads is very important. And then reassembling a cylinder head, again, this is something we will do out in the lab. Now, don't forget to do these quizzes right here in this section. Also, don't forget the media gallery. There's plenty of videos that I'm not going to cover that you can watch to help explain these concepts better, okay? Every section right here is accompanied by several videos, all right? So watch these videos. These are for you. Images, animations, all this is here, okay? So we're going to move on from cylinder heads. We're going to move into engine blocks right now, okay? So remember, cylinder head, top end, engine block, bottom end, all right? So here's our engine block components. Describe the block and its related components. Let's watch how blocks are made. This will explain how blocks and also cylinder heads are made right here. After this commercial.
Motor Mechanics Lesson 1. Car engines work by internal combustion. Air and a drop of petrol enter the cylinder. The piston moves upward, compressing the mixture. The spark plug ignites the fuel, causing an explosion that drives the piston downward, powering the engine. Engine components are housed in what's called the engine block. It arrives at this plant partially made. Here, the cylinder bores, the holes in which the pistons move up and down, are finished off by machining. The tool carves a criss-cross pattern on the cylinder bore walls. Lubricating oil will cling to the grooves in this pattern, enabling the pistons to move smoothly. After machining, the engine block travels upside down to the engine assembly line. When it arrives, a scanner records the block's traceability code, a barcode that enables the factory to track the block through every stage of production. As the engine block travels down the line, devices ensure that each component is installed properly. Elsewhere in the factory, the crankshaft is slowly taking shape. The crankshaft is a bar that's rotated by the up and down motion of the pistons. As it turns, it transfers power to the transmission. The crankshaft starts out as a roughly shaped steel forging. Robotic arms pass it down the line from station to station, until, 20 tooling machines later, it's fully formed. Next, a steel disc with teeth called the reluctor ring is installed. It's heated and pressed onto the crankshaft. As it cools, it shrinks to a tight fit. This ring helps time the combustion cycle. As it spins, its teeth pass in front of a sensor, which reads the crankshaft's position and tells the engine to fire the spark plug at precisely the right moment. Now workers balance the crankshaft. If it's off kilter, the engine will vibrate. A computer analyzes the spin and determines whether they need to drill out metal at certain points to achieve equilibrium. Back on the engine assembly line, the engine blocks are still upside down. A robot lubricates the four bearings on which the crankshaft will turn. Then it drops the crankshaft into position. Pistons come next, 6, because these are 6-cylinder engines. The pistons are made of aluminium. Robots install them into the cylinder bores of the engine block. A steel connecting rod attaches each piston to the crankshaft. Now workers can close up the back of the engine block. A robot applies sealant to the rear cover. Workers bolt it on manually with a tool called a multi-spindle torque gun. On another line, they assemble the two heads that'll cover the top of the engine block. This robot applies sealant to spark plug tubes before inserting them into the heads. The head heads cap off the cylinder bores. They provide each cylinder with a spark plug and 4 valves, 2 for allowing the fuel mixture in and 2 for releasing the exhaust. The black tubes running front to back are the camshafts, the components that open and close those valves. There are 4 per engine. A robot applies sealant and then bolts a cover onto the front of the engine block over a component called the timing chain. This chain connects the crankshaft to the camshafts, so they rotate in unison. This ensures the valves open when the pistons are in the right position. All pretty complicated stuff. Now we can all look bemused next time we pop under the bonnet.
Okay, so again, that was just kind of how everything was made in machine work, et cetera, et cetera. Okay.
We're going to start building the engine. And we'll start with the engine block. It's also called the cylinder block or just the block. We'll call it just the block for simplicity. So the block is a huge part, it's the biggest part of the engine. It's usually made of cast iron or cast aluminium, increasingly aluminium lately. And the block has, its main function is to house the cylinders. And the cylinders is where the piston slides up and down. So that's the primary purpose of the block. It also incorporates passageways for the coolant and for the oil. So the coolant circulates around the cylinders, keeping them cool because they get very hot during the combustion process. And oil circulates through the block to the various places it's needed on the engine. The other purpose of the engine block is it holds the accessories or the auxiliary components for the engine. Things like the alternator, the water pump, the starter motor, the AC compressor. All of those components generally mount to the block because it's good and strong and it can take the weight.
MasterCard is working alongside Black women business owners with ways to get more businesses online and hundreds of millions in funding. Shop their businesses and start something priceless.
This could be you. Binge watching the ocean. Crushing on your favorite character. Tuning in to the people you love. When you're ready, we'll be here. To new memories. Hilton.
This engine block is made from cast iron, which has been the predominant method of manufacturing engine blocks for the last 100 years or so. And the very first engines, very early engines, used individual components, individual cylinders, and a network of brass pipes for oil and coolant, very steampunk-looking engines. But those were extremely hard to mass produce, very expensive to make. So when mass production came along, casting engine blocks, which incorporate the cylinders, the oil passages, the main saddles for the crankshaft, all of those made it cheaper to mass produce engines. So for a long time, engines were cast from cast iron, and if you take a look at the surface of an engine block, it's rough, and that's the texture of the sand that's inside the molds from which this engine block was formed. In the last 20 or 30 years, it's become much more common for production engines to have an engine block that's made from aluminium alloy with magnesium or some other alloy. And the reason is those are much lighter. So an aluminium block weighs about 30% the same block in cast iron. It's a massive weight saving. So for manufacturers who are looking to achieve fuel economy or performance, an aluminium block is the way to go. There's one other type of engine block, which is a billet block, which you would only really find in a one-off in the racing world or for restoration. And this is where a block of aluminium is taken, or just a solid block, and the engine block is milled out of that block with all the metal that's not needed basically machined away or drilled out using a milling machine. That's very expensive to do. So you're only really going to find that in the performance world. But in production engines, cast iron, cast aluminium alloy, that's what your engine block's made of. Once the engine's been cast, it's got this rough finish that you see on the unfinished edges. And then it's machined on the surfaces which are important, which join to other parts, or for example on the cylinders. Those parts need to be machined to make them perfectly smooth. I've put the engine on a stand and rotated it round so that we can see the top surface and the cylinders. The cylinders are made in a block. If it's a cast iron block, then they'll be machined directly into the block. If it's aluminium alloy, then it's likely that there will be holes bored and then cylinder liners will be inserted, or those cylinder liners will be inserted into the mold, and then as the aluminium is poured into the mold, it bonds to them and that contains the liners. With aluminium alloy, there's another option, which is a chemical coating which is applied to the cylinders. Nikasil is one name. And that has a similar function to a liner. The reason that liners are used on aluminium is that cast iron is a tough metal which can take the wear and strain on these cylinders. Aluminium, it's much softer, and so a cast iron liner will be inserted. Now, you might also find cast iron liners that are used to repair problems with cylinders. Let's take a look at the surface inside these cylinders. And the surface on a cylinder is vital because the piston moves up and down. We want minimal friction, and the piston must run on a film of oil. We don't want the piston rings to contact the cylinder wall at all. Now, on one hand, we want the cylinder wall to be perfectly smooth to minimize friction. On the other hand, if it's too smooth, then the oil simply falls off the walls. So we need a fine grain in there to provide some sort of grip for the oil. So what you'll find is there's a crosshatch pattern inside a cylinder on the walls, which is formed by a process called honing. And really, we want a sort of 60-degree crossover of lines on the wall there to form a very fine diamond shape with indentations that can form pools of oil on which the piston rings can run. I've rotated the engine round again. This top surface is called the deck. This is the surface that mates to the bottom of the cylinder head. In between this and the cylinder head, there'll be a gasket. Here's the old gasket from this engine. So that sits there, and it's the gasket that forms a seal between these two surfaces. So it's important, it's vital that the deck is perfectly flat so that we've got a gas-tight seal, because the top here, this is essentially the combustion chamber. There's enormous gas pressure inside this cylinder at the top, and the head gasket takes the brunt of that pressure. So the head gasket it can conform slightly to an uneven surface, but the top surface here needs to be perfectly flat, and the underside of the cylinder head also needs to be perfectly flat. Now, the engine block is so massive and so tough that it's unlikely to warp. The cylinder head sometimes can warp, and this surface will need to be machined down to make it flat again. But the deck of the block, that's much tougher, and it's less likely to need machining. Now, for an inline 4 and inline 6 engine, there's just a single deck. But if you've got a V-shaped engine or a W-shaped engine, then there's multiple decks. There's one deck for each cylinder head.
Now, a thing to add about the deck, if you have an aluminum engine block, it may need resurfaced just like a cylinder head. Again, you need to use the straight edge feeler gauge, look at the engine specs, and see if it needs resurfaced. Excuse me, you can resurface an engine block, the deck, just like you can a cylinder head. Some places can do it in the car, otherwise you have to remove the engine. And by that point, it might as well be either rebuild or replace the engine time. So again, this is something you have to inspect.
And if they need to be machined, then they all need to be machined to the same height. Inside the block run oil passageways, which are called galleries. A lot of people call them galleys, but that's completely the wrong word. A galley is the kitchen on a ship. So these are galleries, and what happens is we have an oil pump here on the front. I don't want to go too much into the lubrication system because we're going to talk about that in another video. But we need to roughly understand how this works. So the oil pump is going to pump oil out of the sump down here, up a pipe, and then in here, which is the feed pipe into the engine block. The oil is going to run along here. It comes to the outside of the oil filter, works its way through the filter, goes through the inside of the filter, and then into here, which is a drilled out passageway which runs all the way through the block here. It enters here, and it goes all the way through and then leaves here. And this oil, this main gallery here is the main supply of oil to the rest of the engine. So from this main gallery, we also have a gallery that runs up here and out through a hole here in the deck, which goes up to the cylinder head and lubricates the camshafts and the valve train. And on there, there's an oil pressure switch. In this case, it's just a switch, which is triggered by low oil pressure and flashes on a warning light on your dashboard. More advanced engines, you'll find a pressure sensor. So that's the main oil gallery, and from here we have little oil passageways, which we can show you, which run down to the main journals and to the jets, which lubricate the inside of the cylinders. So if we take a look at the deck, the oil comes up here through this gallery, and then we've got a oil regulator here, which is a narrow hole, which keeps the pressure in the block nice and high, low down. It's a constricted hole. It's hard for the oil to get through, so that maintains the pressure down here. But that also supplies the oil that's needed to the cylinder head. And then once it's been used in the cylinder head, it makes its way back down through the block, through these return pipes, which basically just drop the oil back down into the sump, and it makes its way around again. So that inside the engine block itself, the lubrication mainly happens on the underside. So I'll rotate this around and we'll take a look at the underside.
With the timeless protection of ADT, it's safe to say...
Hey Google, unlock the front door.
Having brought the engine block round here, we can see the underside. So the engine's upside down basically here. And what we've got is we've got these main saddles, which is where the crankshaft sits. It's vital that these get a good supply of lubricant, because the oil not only works here in this bearing, but it also works its way through the crankshaft, which we'll see later. Anyway, there's holes drilled from here down through into this main gallery here. So the oil comes from the main gallery out through these holes where it pumps into these bearings.
Now he's mentioned a bearing before a couple times. So what is the bearing? Well, if you look right here where I'm putting this red arrow, one there, one there, one there, one there, and one down here by his finger. Those are called main bearings, and that's where the crankshaft rides. There is a bearing, which is a thin piece of metal that's shaped in the form of a half circle or a C, that one half goes in one of these, the other half goes in what's called the main bearing cap, which is the cap that goes on each one of these to hold the crankshaft in. Now, bearings are used, anything that spins, we need a bearing. You have ball bearings, you have roller bearings, wheel bearings, transmission bearings, things like that. But an engine, we tend to use flat pieces of metal as bearings, and these flat pieces of metal are engineered to grab and hold on to oil. Okay, and then the oil is the lubricating surface that the crankshaft rides on, camshaft, etc., etc. And like he's pointing to, these holes right here, that's how oil gets into these main bearings to lubricate where our crankshaft is spinning.
We've also got on this engine, which is quite an unusual feature for a fairly standard engine like this, is we have jets which receive a flow of oil and spray that oil onto the underside of the piston. And that lubricates the wrist pin of the piston, or the gudgeon pin, and it also keeps the piston cold and lubricates the cylinder walls. In other engines, you'll find that as the crankshaft spins, I know we're upside down here, so it's kind of hard to visualize, but the sump would be here and the oil would be sitting in there. The crankshaft would be spinning, and that oil gets flung up and coats all the inside of the engine. And that's what we want. We want the inside of the engine to get a good coating of oil. These jets on this engine, they help that process. So I think what we'll do, let's put the first parts onto this engine block, and we'll bolt on these jets that sit here and lubricate the inside of the cylinders. So we're going to install these jets. There's 4 of them, one for each cylinder, and they've got a little locating pin in there. So we'll just drop that in, and I believe there was supposed to be brass washers, but there's certainly no sign of any brass washers when these came off the engine. In any case, we're only going to end up with oil leaking where it's supposed to be anyway. So let's drop that in there and find out the torque specifications for these. So you can see here this oil jet sprays onto the inside wall of the cylinder and to the underside of the piston. So we'll just tighten this down hand tight and then torque it down with a torque wrench. So I'll just install the other 3 jets, one for each cylinder. So what we've got here is, this is the engine, it's upside down, and the crankshaft sits inside this bottom area of the engine block. And this bottom area that holds the crankshaft is called the crankcase. So the other thing that's interesting about the engine block is that these main caps, there's 5.
So these are the main caps he just put on. And again, each one of those, you've got 2 bearing halves or bearing shells. He didn't put that bearing in, okay, on these. And obviously he's not building this thing to run, but you have to remember to put the bearing in before you put the crankshaft in, and then put the second half of the bearing in the main cap, put it on and bolt it down. Now these main caps have to be kept in order. Like so many other parts of the engine, they have to be kept in the correct order and facing the right direction. Otherwise, bad stuff happens.
I have on here that clamp the crankshaft into the saddles and hold the bearings inside. It's essential that these have a perfect circle, a perfectly round, perfectly dimensioned bore on the center. And these are cast as part of the block and then bored through all the way through the block, all the way through all 5 of these. And then they're cut off and machined on the ends. And that's my understanding of it anyway. And so what you need to be careful of is that these go back onto the right places, because they're actually formed as part of each one of these saddles. So the main caps need to go back on in their original places. And generally they're numbered, but if they're not clearly numbered, you want to mark them with dots or stamped marks in some way. We pop that back off for now. The other thing that goes on the underside of the engine, don't forget we're upside down here, is the sump or the oil pan, which fits on here, just about there, lines up with its holes and holds the oil. Now we'll talk about this later, but just for now, that's another thing that mounts to the engine block. And on the underside, you may find a gasket. On this engine, we just have an instant gasket, some form of instantly cast adhesive gasket. So that's that. Let's turn the engine back over and talk about the core plugs. On this side of the block, we've got some plugs. These holes, which are plugged, these plugs are called core plugs. Now, a lot of people call these freeze plugs. They're commonly called freeze plugs or expansion plugs, and you'll find them in parts catalogues and places listed as that. But they're nothing to do with freezing, really, and it's a common misconception, really, that if the coolant inside the block freezes, then these plugs are designed to pop out. Maybe that would happen if the coolant froze, but realistically, you're going to still suffer some serious problems, most likely, and the block may well still crack. However, freeze plugs, expansion plugs, that's kind of what they're known as, but core plugs is what we're going to call them, because that is what they are. And the reason that they exist in the first place is that when the engine is cast using these sand molds, molds are inside, and the block forms around that mold, and there needs to be some way to get the sand out of the block, and that's what these holes are used for. The engine is kind of tipped up and the sand is emptied out and washed out, and that leaves us with these spaces inside here for the coolant to run. But the remnant of that is these holes, which are then plugged with these thin metal core plugs. I like to think that when this casting process was first developed, some factory somewhere, a couple of guys were working there and they produced this. And they said, "Oh, what about these ugly holes? What are these?" And someone thought, "Oh, yeah, we've got to make these are not a bug. These are a feature. If anyone asks, that's in case the engine freezes, the coolant will expand and the plugs will come out. We call them freeze plugs." So that, in my mind, is how they ended up being called freeze plugs. But that's the way they are. They're a little different from the oil gallery plugs. If you look at the end of the engine here, you can see we've also got a plug here. And this one's for the oil gallery. So oil gallery plugs tend to be small, and on oil galleries, and core plugs will be bigger and all over the place. The other thing to note is that these are thin metal. This block is good solid cast iron or cast aluminium, but these core plugs can corrode, and so it could be a common place for leaks. If your engine block is leaking, it's more than likely the core plug rather than a crack in the block. Luckily, because they're fairly easy to replace, and they're roughly standard sizes as well. While we've got the block round in this position, let's talk about the engine mount, which on this car mounts to these 1, 2, 3 bolt holes in the block. The block's a good place to mount the engine to the chassis. It's super strong, it can definitely take the strain. So on here bolts an engine mount, and that has a rubber mounting which sort of reduces vibration between the engine and the vehicle body. There's various other holes and mounting holes here. These are called bosses, where the surface is machined flat to create a nice flush finish, and the hole is tapped out to give a thread to mount things to. So things like the water pump, the alternator, the air conditioning pump, anything like that is going to be mounted to the block. It's a good, strong component. The other function of the engine block is to provide the cavities for the coolant to circulate and cool the cylinders. The reason we need to keep the cylinders cool is because if they get too hot, then the mix of fuel and air can pre-ignite. That is, it can ignite itself before we want it to, before we create the spark. That causes all sorts of problems with timing and stress on the engine components, so it's something we really want to avoid. The other reason is generally when parts become too hot, or generally when they become hot, they expand and that increases wear. So we want to maintain the clearance between the piston and the cylinder wall. And if the cylinder becomes too hot, the piston expands and we can have contact, metal-to-metal contact inside, which we want to avoid. So we're going to circulate coolant around the cylinders through these voids, and generally it's going to flow from the bottom up or upwards. Hot liquids rise above cool ones, so the general flow of coolant you'll find will be from the block of the engine up into the head and then away either from the front or the back, depending on the flow arrangement, and back around through the radiator. A well-designed coolant system should have no air gaps, no voids inside that the coolant can get trapped, because when you drain the coolant system, you want to drain all the coolant. You don't want to find little reservoirs of coolant left in there. So that's one thing. It's a similar situation with the oil passages.
So there was a pretty thorough explanation of what an engine block is, does, looks like, the passages inside of it. Okay, I've got a couple other engines, another video of an engine block right here. You know, we're going to skip that one. You guys can watch it on your own. I've also got a engine noise diagnosis right here, a video on how to help find engine noises, which we'll talk about later, but that would be a good video for you guys to watch. The rotating assembly, what is the rotating assembly? The rotating assembly is what spins inside of an engine block, and that is the crankshaft. The crankshaft rotates. The pistons and connecting rods move up and down. The crankshaft rotates. So let's scroll down here to the media gallery right here, and let's see if we can find our rotating assembly right here.
The crankshaft is attached to the connecting rod in offset areas called throws, where the downward power pulses change into rotating motion. Crankshafts must be strong enough to do this without bending or twisting. They are a one-piece casting or forging of heat-treated alloy steel of great mechanical strength. Counterweights are formed to balance the throws and also the big end of the connecting rod. Fine balancing is done by drilling out or adding small weights. The crankshaft rotates in the engine on journals which run in bearings called the main bearings. The connecting rod with its big end bearings are attached to the crankshaft crank pins located on the throws. Drilled passages carry lubricant under pressure from the main bearings to the adjacent big end bearings. The rear of the crankshaft is drilled and tapped for flywheel attachment. Near the front of the crankshaft, a timing gear or sprocket is attached to drive the camshafts. A drive pulley is mounted on the front of the crankshaft. It drives many components, including the alternator, the fan and water pump, and power steering. Many inline and V engines have a harmonic balancer attached to the crankshaft. The harmonic balancer is more correctly called the crankshaft torsional vibration damper. It prevents crankshaft vibration. In most cases, the harmonic balancer incorporates the drive pulley.
Okay, so again, there was our crankshaft, which is part of the rotating assembly. Bearings, let's watch bearings right here. Yes, we have crankshaft bearings, but we also have the same type of bearings throughout the engine, again, for camshaft, connecting rods, etc., etc.
No engine can run without bearings. Bearings are used in engines to support and protect rotating parts and allow them to turn freely. The connecting rod must be able to spin freely on the crankshaft, and the crankshaft must be able to spin freely in the engine block. Connecting rod bearings and the crankshaft main bearings are called split sleeve types, which means they are in two halves, called inserts, slippers, or shells. These precision inserts have a steel back with a very thin layer of bearing material bonded to it. The bearing material is an alloy that can include metals such as tin, lead, aluminum, and copper. Bearings designed for light duty may be made of white metal. It's an alloy of tin and lead with small amounts of copper and antimony. Alloys of tin and aluminum improve the load-carrying capacity for intermediate applications. Copper-lead alloys give even more improvements. They're used in applications such as diesel engines and high-performance vehicles. Bearings need a difficult mix of properties. They must be hard enough to resist wear, but soft enough not to damage the shaft. The soft bearing surface also allows any hard abrasive particles to become embedded in the surface. They can become so deeply embedded, they are prevented from touching the rotating shaft by the film of oil. It is the mix of metals, tin, lead, copper, and others, into an alloy that makes this combination of hardness and softness possible. In a main bearing, the upper half of the bearing fits into a machined section of a crankcase web. The lower half is carried in the bearing cap, which bolts onto the crankcase web. In a connecting rod bearing, its upper half is carried in the big end of the connecting rod. The lower half is in the connecting rod cap. One main bearing has thrust faces which accept the end movement of the crankshaft. These can be in the form of flanges that are part of the bearing. Alternatively, a separate thrust washer can be fitted into a machined recess in each side of the bearing cap. Sometimes a mating recess for each side is machined into the cylinder block and mating halves fitted to both. Under normal running conditions, spinning shafts ride on a microscopic wedge of oil. Oil flows through a long gallery into the cylinder block. Each main bearing has its own oil supply passageway from this gallery. Passageways drilled in the crankshaft carry oil from the main bearing journals to rod journals. It maintains the oil wedge between the shaft and the bearing and carries away particles that could cause wear. Engine manufacturers specify the clearance required between the bearing material and the crankshaft. This clearance gives the best combination of oil pressure and flow. As clearance increases with wear, oil flow increases, causing oil pressure to drop. Then the shaft may rub against the bearing surface and wear even faster.
Okay, so there was bearings. So again, camshaft, crankshaft, connecting rods, they've all got bearings in there. And again, lots of videos in here as far as the parts of the bottom end, the parts of the block. Okay, so use this media gallery right here. Okay, I've got several videos in here. Piston design, the different types of pistons, connecting rods, the different shapes and designs of connecting rods, how to properly size engine bearings. Yes, I'll talk about some of this out in the lab, but these are a lot more in depth for you to use. I've also got a video of an engine knock. This is what happens when a bearing goes bad. So it sounds terrible. That's actually a former student's vehicle from several years ago. He was really hard on this vehicle. He didn't care about it. It was grandpa's money that fixed it. It went through like 3 or 4 engines in 2 years of high school for him, and probably as many transmissions. But that knocking sound, that's what happens when a bearing is completely worn out, completely gone. The longer you drive with that knocking sound, the worse stuff is happening in that engine. Okay, this is full rebuild time. There's not something in a bottle to put in to make this go away for any amount of time. Okay, also got a video of a spun bearing right here. Again, what happens when bearings go bad. I've got an engine tear down right here video of a 2JZ engine being taken apart. Okay, I've got an engine block inspection video right here. Again, this is some stuff we'll do in lab, but these videos are here for you to use to help you understand this stuff. Okay, the media gallery, don't forget to use it as well. Quizzes, don't forget to take these quizzes. And that's pretty much it for cylinder heads and engine blocks. Otherwise, we're pretty much done with this lesson right here. And, you know, like I said, take advantage of the media gallery. Don't forget to do everything. Don't forget to try to do everything to your best ability. Otherwise, I will see you guys out in the lab.